So welcome. Uh, in this session, I will show you Apache TinkerPop and also some demo with its query language Gremlin. Uh, who knows a little bit about graph database here? Raise your hand. Okay, cool. Who is familiar with Gremlin query language? Okay, less people. Cool. So let me introduce myself. My name is DuyHai Doan. I'm working as a technical advocate for Apache Cassandra at DataStax. I'm also committer for Apache Zeppelin, and I am the maintainer of the Zeppelin Cassandra interpreter. So Zeppelin is just a notebook like this, right? I'm working for DataStax. So who is DataStax? We are a company offering DataStax Enterprise, which is the commercial distribution of Apache Cassandra, the open source project. So DataStax Enterprise is we take the open source product and we add extra features. And we also offer DSE Graph, which is a graph database built on top of Cassandra. So why graph databases? Today, in 2017, anyone in this room knows or use one of those applications, right? Twitter, Facebook, YouTube, and so on. And with graph database, the major use cases is how you have a lot of information and how to find a specific information inside this stack, right? You can also use graph databases to find patterns, to detect patterns, to look at the big pictures. Another interesting use case is to analyze the root causes, because in graph database, everything is connected. So you can navigate from one node to another one through different paths. And you can also use graph databases to study how one vertex can impact its neighbors. And about the popularity of graph database, we can see here. So I took a screen capture of Database Engines, which is a famous website listing all the NoSQL technology and graph technologies. So graph technology is becoming more and more popular nowadays. How do we compare graph to relational? So with relational database, you define relation. So here we have a user table, right? Person ID, first name, last name. A movies table, movies ID, title, country. And to create the relationship between the users and the movies, we have the view table. So which person has watched which movie at what time. Right. So relational database, you define relationships between entities, and you store the entities and the relationship in a normalized fashion, right? Joint tables. With graph database, we have this. You have a vertex user, you have a vertex movie, and you have an edge view which define the relationship. We, of course, in graph database, we also store the entities and the relationship. But now with graph database, you can explore your data, and you can also discover unexpected relations. And in fact, the value of your data is defined by how many meaningful relationships you can find between them, right? So in this graph, you can see on the left different topology of databases. You have key value NoSQL database. It is very simple. You have a key, you have a value. In terms of complexity, after key value, you have tabular NoSQL database. So you have a key and a lot of values, like Apache Cassandra. Then you have document databases, where you define your document with their properties. Then you have relational database that everyone knows. And at the end of the spectrum, in terms of complexity and values in the relationship, you have graph databases. Any questions so far? No. So let's move on. Apache TinkerPop. So what is Apache TinkerPop? So TinkerPop is an open source graph computing framework, right? Computing. So it is not a database. It does not store your data. It only help you to compute your graph data. The project has been started in 2009 by some people, and they joined the Apache Software Foundation 2 years ago. So now this is an official Apache project. So what is funny with TinkerPop is you have some cartoon characters here. The most famous being the Gremlin, this bright green toy. So in fact, TinkerPop is in fact a stack of different components. On the top, you have the Gremlin server. So it's a server which helps you to query your graph database. You are using the Gremlin traversal language here in green to query your data. And in fact, because Apache TinkerPop is a very generic framework, each graph database vendor can provide specific strategy, specific implementations. Right? You can define also a user DSL query language specific to your business. This query language will use the core API called Blueprint. And in fact, you have two engines to query your graph data. The real-time engine, OLTP, and the batch engine, OLAP. Right? So with TinkerPop, most of the time the batch engine is using Apache Spark with GraphFrame. So today I'm going just to show you the real-time engine, right? Some quick definition. In the graph databases family, you can find two types of graph database. RDF, based on the resource description framework, and property graph. So for RDF database, you have Allegro graph, Blaze graph, Ontotext, etc. And for property graph, you have Neo4j, for example, Titan, DataStax Enterprise Graph, OrientDB. And this talk will only focus on property graph. So what is a property graph? A graph is defined as a set of vertices, nodes, and edges, which are the arcs. Right? So the formal definition is a set of vertices and edge. An edge can be directed, so there is a direction from one vertex to another one. An edge is linking only two vertices. So you cannot have an edge that can link three vertices. So it is a binary edge, binary direction. Of course, an edge can link a vertex to itself. Each edge and vertex can have attributes, right? Here on my user, I have the name attribute and the age. On the movie, I have the title attribute. And I have also categories, which is a multi-value attribute. And the same on the edge. Um, so a vertex is just, well, the topology, okay, just a node. And how can we distinguish different vertex between them? So we assign what we call a vertex label, right? So user is a vertex label, movie is a vertex label. You can understand it as a category of vertex. And the same for the edge. You have edge label, so view is a category of edge, and nose is another category of edge. Edge properties. Now let's focus on the Gremlin traversal language. On the left, you have the graph definition, and on the right, you have a metaphor to the hardware. Right? A graph is just a bunch of data on disk. The traverser, so this Gremlin cartoon, is in fact the CPU, one CPU thread, right? And what we call the traversal, in fact, it is your program. It is your query. Right? So let's give some example. This is my graph here. I have a person, I have movies, and I have users, right? So one person can be an actor of a movie and can be also a director of a movie. So I want to know all the movies in which Harrison Ford has played as an actor. So what is my query? How can I query my graph database using Gremlin to answer this question? So I start with G. G means graph. This is my graph, right? It is an alias to my graph. J.V. V means, oh, now give me all the vertices in my graph. So at this step, J.V, the answer of J.V is all users, all person, all movies. Because I didn't specify what kind of vertex I want. Now let's be more specific. J.V.has label person. Okay, now I'm not interested by users or movies vertices, but only by person vertices. Right? Has label person. So now I specify the type of vertex I want. Has name Harrison Ford. It corresponds to a filter, right? I am only interested in person vertices whose name is Harrison Ford. And now, from the person, I want to navigate to the movies. I want to fetch all the movies of Harrison Ford in which he was an actor. So I'm using this edge, out actor. So from person, I'm going out of person using the edge label actor. Okay. You specify the direction, right? Out and not in. So I'm going out of person into movie using the edge label actor. Okay, so now from Harrison Ford, I access to all his movies as an actor. And that is the answer of my question. So I will have a collection of movies in which Harrison Ford has played as an actor. Okay. Now let's make it a little bit more complicated. Give me all movies in which Harrison Ford has played as an actor with the mean rating greater than 7. So because each movie is rated by users, right? And I want only movies with the average rating greater than 7. So now I add an extra filtering, the where clause. So now at this step, out actor, we are located here, right? The traverser is here, is at movie vertices. Now I said, where in edge, like, so take all the incoming edges with label like, compute, fetch the value rating, compute its average value, and put a condition on this average value. So I want only average rating greater than 7. See? So this is a little bit more complex example. And in fact, you can see that with Gremlin, you are navigating visually from one edge of vertex to the another one. You are describing your navigation in the graph. So let me give you some more example. So it's demo time. In fact, most of this talk is based on practical demo. Select column. So this is my schema. I have another schema. Right? I am using DataStax Studio, which offer me a visual notebook to play with my graph. So this is my graph schema. I have product, items, orders, customers, right? And so on. And for each Gremlin query, I will show you the equivalent with SQL and the equivalent with JavaScript functions. So, for example, select star from categories. I want to fetch all the categories of a product. This is the SQL. If I was using Java stream, Java 8, I would say, okay, from the stream of all the vertices, I filter. I only take the vertices which are instance of category. And then I want to display their toString, assuming that toString will print all the internal fields, right? And then for each of those product categories, I print. And the Gremlin query language is very simple. G.v, all vertices of label category, give me their value map, which are their properties. So here are all the categories, their name, their description, their ID. Pretty simple. Next. Now what if I want to select a single column? Select category name from categories. Okay. In Java, in the map method, instead of calling toString, I will say, oh, I want to only take category name. So category.getName, and then print out the values. With Gremlin, the beginning is the same. Now, instead of calling values map, I call values name. So give me only the name of the category. Okay. You can also select multiple columns, category name and description. So here has label, value map, name, and description. What if, oh, so if we look in the row result set, it is a collection, you see, of name and description. What if instead of using value map, I use values? Let's see what is the output. Okay, now it is a row list of text. Okay. In fact, when you call value map, you have as an output a collection of map. The key are the properties of your vertex, and the values are their corresponding values. Whereas when you call just values, Gremlin will put all the output into a single list. That is the difference. Okay. Here you see the map key value, key value. Now, let's say I want to compute some operation on my column. So select length. What is the length of each category name? So in Gremlin, you have some extra step to do. So when I fetch out the value, now I want to compute the length of each name of the category. So I use the map operator. I transform the name into an integer. So it is pure functional programming. Map it. It in Gremlin means an option of something. So an option of, currently it is a string, which is a name. So it.get will give me the string, and then I compute the length method. Okay, see. Now, how can I do select distinct? I want to have distinct lengths for each category name. Well, for select distinct, it is very simple. I call dedup to remove duplicated values. Now let's look at filtering. Okay, I can select some columns. Now how can I filter my values? So select product name, unit in stock from products, where unit in stock is equal to 0. So give me all the products which are out of order, right? The beginning is the same, has label product. Now we add a condition in the property unit stock of each product vertex, has unit in stock equals to 0. And then we fetch out their name and unit in stock. Okay, pretty simple. You can also query by range. So where unit price between 5 and 10. So instead of having the equal condition, now we have a between condition. So has unit price between 5 and 10. Okay. And if you want multiple condition, multiple where clauses, where discontinuous is true and unit in stock different than 0, you can just chain the has step, giving all products where unit in stock is not equal to 0 and discontinue is true. Okay. So there is a bug in the display here, because in fact, when I switch to the row display, I can see the value of discontinue. All of them equals to true. Right. So there is a little bug here. Now what's about ordering? Select, where, blah, 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 order by. So give me the top 10 product name, unit in stock, from products, order by unit price, descending. So first, in Gremlin, I fetch all the products. I order by. Order them by what? By unit price. Oh, descending, sorry. Desk. Decrementing, order. I take their name, unit price, and unit in stock to display, and limit 10. Okay. So you see here, the 10 most expensive product, right? We can also do grouping, equivalent of group by in Gremlin. So determine the most used unit price. So this is the SQL query. You have a nested select. So select unit price, count star as count from product, group by unit price. So for each unit price, we count the occurrence. And then we select the top one, unit price, order by count. This is the SQL. So the Java stream is horrible. Right? If I was to develop it in Java using Java stream, I need to do all these complicated steps. And with Gremlin, so let's see how I can do this with Gremlin. Give me all product vertices. So at this step, I put in the comments here, what is the result, the output of this step? So g.v has labeled product. The output of this step is an iterator of product. You have an iterator of product. Okay. Group count by unit price. This is a special operator. So it is a count combined with group by. So group count. So I group by unit price and I count. The output of this step is an iterator of map decimal long. Huh? Oh yeah, decimal long. The key of the map is the unit price because I group by unit price. The value of my map is just the count. And in fact, what is interesting here is even though we have an iterator of map, there is only one single element in this iterator. Right. So I have done my group count. Then I want to order. Order by what? Order by count desk. So please pay attention here. There is a trick. If I do a global order, if I do that, order by value desk decrementing, value, well, my ordering will be applied to the whole iterator itself. And that's not what I want. What I want is, I want to order by the value of the nested map for each map. So I need to put the local keyword. What does it mean? Order local means for each occurrence of map inside my iterator, order this map by its value decrementing. So order the map by the count desk. So once I order my map, I select the keys of the map, which are the unit price. And also, I want to take the top one. So again, I want to limit the output. And I need to put the local here, because if I don't have local keyword, it means, well, limit, take the first element of the iterator, which is the map itself. And in fact, there is only one element in the map, so this is a no up. Let's see the result. If I remove the local keyword, what we will see is the map itself, right? Okay, because I remove select, so don't do select. Okay, this is the map itself. And the map is ordered, you can see, by the value. But that is not what I want. What I want is a limit local. So just take the first element of the nested map. Aha, now we have it. And then I put back select keys. So I want only the unit price and not the count. Here we are. So it is really important to understand with Gremlin at each step what is the type of my data. Here I have an iterator product. With the group count, it becomes an iterator of map decimal long with only one instance, and so on. This is Gremlin basic. Now let's see what we can do with advanced Gremlin. Oh, we can do joins. Haha. Welcome to joins. Inner joins. So this is my schema. I put a picture of my graph schema so we can understand where we are going. So the idea is get all products from a specified category. So in SQL, it is very simple join. So select product name from product, inner join categories on categories ID equals to product.category ID, where category name is beverages. So I want to get all products of category beverages. So I just show you the same code in Spark RDD, big piece of code, and in Gremlin. So g.v has labeled category. We start from the category vertex. So the output is an iterator of category. Has name beverage. It is just a filter, right? Select all category vertices whose name is beverages. So in fact, after this filtering, you have only one vertex in your iterator. In category, what does it mean in? So now we start the traversal. Let's have a look at category. Where is it? Okay, here. From category, we have an inbound edge in category. So by saying in category, I'm moving from category to product. Right? So now the output of this step is an iterator of product. And then take their name, values the name. The output is a list of string. So let's execute this. Okay. This is all products of category beverage. Now we can do also a left join combined with group bind and count. It starts to be complicated. So the SQL is select top 10 customer ID, count orders order. So the idea is count the number of orders for each customer, right? So the SQL is select top 10 for each customer and take the top 10. Customer ID, count order customer order ID, from customer left join, group by customer ID, sort by count order desk. Now we have something interesting with Gremlin. This is a quite complex query. I want to express it in a very simple manner. So we have pattern matching. I say, okay, I start with customer. G.v has labeled customer. Now I want to pattern match. Dot match as C. So for each customer we label as C, get the customer ID values and store it as customer ID. And for each C customer, so the trick here is as we give the same alias for each condition, the condition will apply on the same vertex. Right? So for the same customer where we fetch the customer ID, now out order, so we are navigating from customer out order, so we are going from customer to the order vertex. We count the number of order and we save it as orders. And once it is done, we do a select. So select customer ID, which is my alias here, and orders, which is my alias here. The output of this step is an iterator of map string object. Each map is of this form, customer ID and orders. I want to order those maps. How? By orders descending. So I have a lambda step here. Each map, I get the order, and I put a minus in front. So this is a descending ordering on the value of order, which should be count is along something like this. And then I take the top 10. So let's see the result. Okay, here we are, the top 10. If I remove the top 10, I will have all customer with each of them their total number of orders. Okay, and so on. So I have like 90 customer in my graph database right now. Yes. I don't think so. We have limit. We have also, we can take the first 10 or the last 10, but I don't think we have some kind of paging, something like this. Because in fact, when you execute this query, it is lazy. It's like in functional programming and JavaScript, it is lazy by default. So it starts by the end, and then it pulls all the steps backwards. So if you say, oh, I want the next page, it means that you need to compute the first page. So yeah, there is no magic. We cannot compute the next page without computing the first page. Oh, let's do something really crazy. Recommendation engine. Wow. So how to recommend 5 products for a specific customer. So for a given customer, we want to recommend 5 products. And which products are there? The products are chosen as follows. We determine what the customer has already ordered. We determine who else ordered the same products. So those people, we fetch all the order they have done. And we subtract from the order that has the products that had already been ordered by the initial customer. And then we rank the products by the number of times they have been ordered. So the select, the SQL query is something crazy like this. So don't try to understand. Just to give you the idea, okay? If you were to answer this question in SQL, it will finish like this. And now, how can we answer this question with Gremlin? So stay with me. It is a complex query. So we will proceed step by step. J.V has customer ID alf key. So I just take a random customer. So we start from this guy, this customer with this customer ID. We save it as alf key. Out order. So from the customer, we are going out order. So we are going to the order vertex. Iterative order of alf key. Out contains. So from order, we are going out to contains. So we are going to item. All the items ordered by alf key. Out is all the product ordered by alf key. I could not navigate using this edge because this edge is about the rating. I'm not interested by the product rated by the customer. I'm interested by the product ordered by the customer. So I need to go the long way from here to here to here, back to here, right? And when I reach this step, so all the products ordered by alf key, I call the aggregate function. This will save all the products of alf key into a collection named alf key products. So the name is given here. This is an alias, right? Then I'm going back. So I start from alf key. I'm going this way. Now I'm at product. Now I'm going backward to alf key. So in is in contain in order. So from all the products, I'm going back to customer. And now I say, now I want to take all the customer which are not, so which has ordered the same products, of course, but which are not alf key. So we are not equal to alf key. And now I'm doing my traversal once again. So those customers which are not ALF-key, what they have orders. So out order, out content, out is. Take all of their products, the products that they have order, which are not the same as the one ALF-key has order. So I save those products here with an alias to be used here without. So it is like a subtract operation. I have a collection of order. I subtract from this collection the products ALF-key has order. And now group count by name. So from those products, I group by product name. It gives me an iterator of map of string long with only one single element. Map key is the product name. Map value is the product count. Order local, again, because I want to order inside the map and not in the iterator. By value, which is by the product count, descending. Now I select the keys of the map, so I take only the product name. I ignore the count. Limit local 5 unfold. Here are the 5 products I want to recommend to ALF-key. Right? Oh, why unfold? So here in the row display we have this. If I didn't put unfold, I will have this. Right? So just for formatting. So as you can see, the same complex query with SQL. In graph, it is just defining your path. I'm here, I'm going to here, put some conditions, go back, put some conditions, and then extract the properties of the vertices you want to display. And doing some order, group count, and that's it. So it's very visual. And in fact, when you are creating Gremlin queries, Gremlin traversals, you always need to have the schema in front of you to understand where am I in my graph. Let's say, oh, how can I have the top 3 biggest buyer? Right? So a buyer is a customer, has label customer, out order as order, select. So for each customer, I want to have his orders. Select. So this is a very weird syntax. Select customer order by name ID. So the name here applies to the first parameter in the select clause. The second by apply to the second parameter. So select customer by name and order by the ID. So if I stop here, I would see something not very interesting. So for each customer, the order ID, right? If I step my query here. Now I continue with group count. Because after select you have a map, I want to group count. So group by what? Group by select customer. So I want to group by customer and count the number of order, of course. Each customer, their number of order. Now order by value, so order by the number of order, descending, limit 3 to take the top 3. Here we are. The top 3 biggest buyer. In fact, this query, I can do it with another way. The same query, right? Top 5 or top 3 is the same thing, but optimized now. Select customer as, now I give 2 alias to my customer. As customer and as order count. Why? Because now the graph traversal, here I do my graph traversal here directly. And now I want to do my graph traversal inside the select clause. So select customer, by name, customer name, and by customer dot out order count. Aha. And then the ordering clause is the same. So with Gremlin, you have different ways of answering the same question as in SQL. Some query are more optimized than other. The top 3 most rated products has label product. So the same idea. I do my traversal inside the select by and not outside. Product as name and average rating. Select product by name and also by, oh, there is a local here. What does it mean? For each product, I want to compute, I want to go to in edge rated. So for each product, where is my product? Here. I want to go to the edge called rated and take the rating. Take all the ratings for this single product, compute the average. So why do I need this transformation into integer? Because I made a mistake in my schema. The rating, instead of using an integer type, I use a text type. So to compute the average on the text, it's not possible. So I need to convert it to integer first. So for each product, I fetch the rating values from the rated edge, compute the average, and then I order by average rating, limit 3. Okay, so this is the top average rating for products. But in fact, there is something weird. You see, 10. The 10 is the maximum rating. So why do we have 10, 9, 9? In fact, my query is not very well designed. Because imagine that you have some product which has only 1 or 2 ratings. It's not interesting. I want only to take products with a lot of ratings. Because if you have a single rating of 10, the average is 10, right? So I want to exclude all those products which has only 1 or 2 ratings. So how can I do that? With a where clause to filter. So give me all products now where in edge rated count is greater than 10. So all the products which have more than 10 rated incoming edge. Let's see the schema. All the products that have more than 10 incoming edge rated. Where is my... I'm lost. Oh, I'm here. And now the result is very different. Aha. Now my top 3 most rated product is more sensible. I think we are running out of time, so I will not show you the other stuff. So, do you have any questions so far? Yes.
Sorry, I didn't quite get what I need actually TinkerPop for, because I can already run all these pairs, let's say Neo4j.
Oh, Apache TinkerPop is a framework. And in fact, right now, you have many graph database vendor which support TinkerPop. So in my, I think in my first slide, I listed some of them. So Neo4j support, you can do this kind of query with Neo4j because Neo4j support Apache TinkerPop. TitanDB support Apache TinkerPop. Of course, DataTags Enterprise support TinkerPop because I'm doing my demo with DataTags Enterprise Graph. OrientDB also support Apache TinkerPop. There's some thing you should know is the kind of support. Sometimes the support is 100%. Sometimes they support only a limit, a subset of the features. So you need to check. Other question? Yes. Oh, it is groovy. Yeah.
And how are the strings that are parameters mapped to classes? Like if you say has label customers, you say that the result is an iterator of customers.
Oh yeah, it is a filter. It is a filtering. I have done this in the first notebook. It is a basic Gremlin. Yeah. This when you say has label, so g.v is oh give me all the vertices, all of them. So you can have millions of vertices. Now you say has label category. It is a filter like oh this vertex instance should be of type category. So it is a kind of filtering, but a special filter on the type of the vertex and not on its properties. Is it clear now? Yes. Can a vertex has a multiple label? No, because in fact, when you put a label to a vertex, you define its type. So you cannot have a vertex being a product and I don't know something else. It's weird. So you can have multiple properties, but the label is a single one. Other question? No? Yes?
I would have a question. So you mentioned that this language, this query language, was easier and it can go in the graph back and forth
Yes.
and collect everything. So the question is, how does this play with performance?
Excellent question. What's about performance? Okay. Dot profile. We have the same thing like in SQL profiling. Okay, for each step, you see you also see the SQL query in Cassandra because DSC graph is based on top of Cassandra, which is the storage engine. So when you call the profile step, it will show you the profiling and you can see what kind of query is done internally. So you can understand, oh, this is not an optimized or this is optimized and so on. We also have explain. So this is profiling for performance. You can see each step, the duration in millisecond for each step. And you can have also explain. So you have all the tools to optimize your query. Other question? No? Thank you.